Today, we are going to be making a galvanic cell using magnesium and iron. A galvanic cell works by a redox reaction between both of the metals. This means that one metal is losing electrons, magnesium in this case, and one metal is gaining electrons, which would be iron. The redox reaction between these two metals causes an imbalance in the charge of each solution, with the magnesium solution growing more positive as time goes on, and the iron solution growing more negative. The issue with this is that the imbalanced charges will eventually cause the redox reaction to stop once enough opposing charge has been built up. To circumvent this, we'll be using a salt bridge in order to allow free movement of ions between the solutions so that the charges can equalize. In order to make this cell, you'll need one 100 ml graduated cylinder, 3 glass stirring rods, 3 scupulas, 350 ml beakers, a strip of iron, a strip of magnesium, a mass balance, scissors, a voltmeter, 2 alligator clips, a coffee filter, 9 grams of iron 3 nitrate, 20 grams of lithium chloride, and 5.5 grams of magnesium nitrate. First, put about 9 grams of iron 3 nitrate in a beaker. Then, put about 5.5 grams of magnesium nitrate in another beaker. And last, put 10 grams of lithium chloride in your final beaker. Pour 50 ml of water into your magnesium and iron beaker to make a 0.75 molar solution and stir until fully dissolved. Pour 100 ml of water into your lithium chloride beaker to make a 2.5 molar solution and stir until fully dissolved. Now, grab your coffee filter and cut it in half. Roll up 1/2 of your filter and place into the lithium solution, making sure the filter is fully submerged. Place your magnesium strip into your magnesium solution and your iron strip into your iron solution. Grab your voltmeter and your alligator clips, connect the positive side to the iron and the negative side to the magnesium. Then, place your rolled up filter between both of the solutions, making sure it is touching both liquids. Now you should see about 0.9 volts in your voltmeter. However, as you can see, we only got about 0.6 volts. So let's see how we can fix that. If you're getting a low voltage, your metal is most likely a little dirty. So grab some steel wool and scrub both sides of both metals. And now we have 0.9 volts. If you still have a low voltage even after cleaning the metal, you can try a number of other things. Make sure your metals are in the correct solutions, iron in the iron, magnesium in the magnesium. Or you can try replacing your wires, as sometimes faulty wires can be the issue. Now let's talk about changing the voltage of this cell. In order to change the power level of this cell, there are about 2 ways to do it. The first way is to simply add or remove salt from your salt bridge solution. In our testing, we found that low salt concentration in the bridge dramatically reduced the voltage output of the cell, and high salt concentration showed a dramatic increase in voltage. However, it was found that increasing salt concentration only increased the voltage until about 2.5 moles per liter, where the voltage plateaued with any added concentration. In order to further increase the output voltage, it is also possible to increase the concentration of the solutions themselves, as the concentration used in our experiment was only about 0.75 moles per liter for both metals. This method has similar limitations to the aforementioned salt bridge method, where the voltage eventually plateaus after a concentration higher than 1 mole per liter. This plateauing effect may be due to a bottleneck within our system. Some culprits for this bottleneck could be the wire's resistance, the salt bridge concentration, or the metal surface area. However, we believe that the most likely explanation for the bottleneck is temperature. Increasing salt concentration and metal ion concentration can only increase the voltage to a certain extent, but increasing temperature has the potential to even further increase voltage output. Fun fact: galvanic cells have many medical uses because of their portability and condensed design. An example of this is the batteries used in pacemakers. Welcome to Chapter 2 of this educational video, where I'll be discussing the issue with electric vehicle batteries and their future solutions. Most electric vehicles in the market today use large lithium-ion batteries to power their drivetrain. Lithium-ion batteries are very similar in design to the battery we created in our experiment. They have a metal anode and cathode and include a porous salt bridge which allows lithium ions to pass through each side of the battery. The only difference, however, is that lithium ions use almost pure graphite on the anode side of the battery. Graphite is what allows lithium-ion batteries to recharge so effectively and with so many life cycles. To recharge a lithium-ion battery, power is put back into the battery and lithium ions pass in the opposite direction from when they are recharging, so they move from cathode to anode, to collect in the crystal lattice structure of the graphite anode. Lithium-ion batteries' rechargeability and long lifespan is what has caused it to become the primary choice of battery for commercial electric vehicles. Although lithium-ion batteries are favorable when compared to other conventional battery choices, there is still one major drawback. Lithium-ion batteries explode. On the periodic table, lithium is listed as the third element and therefore has one of the smallest atomic radiuses of any other type of metal. This small radius causes lithium to be violently reactive with pretty much anything. If exposed to oxygen, lithium will spontaneously combust or even explode, and if exposed to water, it will produce an abundance of heat and create flammable hydrogen gas and toxic lithium hydroxide gas. This is a serious problem for electric vehicles. Lithium's intense reactivity creates the needs for EV batteries to be completely sealed and watertight, and if anything were to compromise that seal, bad things would happen very quickly. In the event of a crash or just long-term wear and tear, the lithium-ion battery in a car has a serious possibility of creating a fire or even exploding. There is a solution, however. Solid-state batteries have been expected to replace typical lithium-ion batteries in electric vehicles within the near future. These batteries do not use liquids within their designs and instead opt for a solid for their ion solution. Typically, ceramic or silicone is used as the medium for ions to move throughout the battery. The benefit of solid-state batteries is that lithium atoms are encased in a solid which dramatically reduces the reactivity and increases the thermal stability of the battery. This means that SSBs will not explode in the event of a crash or a puncture and will have an overall longer lifespan because of less reliance on a perfect seal in the battery. Aside from just safety, however, solid lithium batteries also have the capability to hold a longer charge and to be charged faster than a regular lithium-ion battery. A Tesla Model S that has a lithium-ion battery with a capacity of 100 kWh and 640 kilometers of range takes about 9 hours to fully charge. If the battery was replaced with a solid-state lithium battery, it would have 50% longer range and take only about 30 minutes to fully charge. Overall, current electric vehicles are limited in both safety and practicality by their lithium-ion batteries and are not expected to be used if electric vehicles are going to dominate the vehicle market. Car companies like Toyota and Tesla have already announced that they will be releasing vehicles with solid-state batteries by 2025, which reveals a bright future for electric vehicles. Thank you for watching this video.